As a housekeeping rule, I would like to request you all to mute your microphone during the presentation. The presentation will run for 30 minutes and 15 minutes after the presentation is allocated for the question and answer session. Now, I would like to welcome and introduce our speaker for today's webinar, Dr. Pawat Busal. Dr. Busal is a pharmaceutical scientist and has been working in drug delivery and pharmaceutical product development in human and animal health and manufacturing for the last 16 years. Currently, he is working as a product development team leader in a biotech company situated in Hamilton, New Zealand. Following his doctoral degree from the University of Auckland, New Zealand, Dr. Busal has also worked as a research fellow at the Otago University, Dunedin for the Bayer and Elanco. Before moving to New Zealand to pursue his PhD, Dr. Busal was working in Omnica Laboratories, Nepal. His work has been central to sustained release drug delivery system with interface engineering, microbiology, medicine, and veterinary science. Dr. Busal has been interested in both fundamental and commercial application of drug delivery research. He has actively contributed to several generic commercial pharmaceutical products, journal publications, conference presentation, and has over 7 issued and pending patents worldwide. We are very pleased to have him today. And now I'd like to request Dr. Busal to present his talk. Thank you.
Thank you, Subhisha. I should have sent a short biography. Apologies for that. So thank you, Prozul. Thanks for inviting me. I'm really glad to meet you all. So wherever you are, namaste, everyone. So it's I hope it's summer over there, but it's a cold winter over here in New Zealand. So today I'll be talking about the biodegradable polymers. Before jumping into that topic, as Subhisha said, my work has mostly into drug delivery research. And as this is a burgeoning topic, it's a very big topic. Most of the polymers which I'll be talking about will be through the lens of drug delivery. But as it touches a lot of discipline, and I will mention some other applications as well. So, so shall I start, and shall I share my presentation?
Yes, please.
Yeah. Okay. All right. So yeah, so this biodegradable, as I said briefly, biodegradable polymers, it's a very burgeoning topic these days. It's talk about biodegradable, sustainable polymers, green polymers, and everything. The reason why this topic has become so important is that because of this non-biodegradable polymer, there are a lot of issues happening around the world. The non-biodegradable plastics are not degrading. It has contaminated sea. It has entered everywhere. So before moving into biodegradable polymers, I'll just mention about why we should look for the alternatives. The problem with non-biodegradable polymers is that it is very tough for the microbes to break. So global production of plastic is around 360 million metric tons. It's the data published in 2020. Nepal Nepal produces about 2.7 tons of plastic, which is mostly non-biodegradable. And I got this data from EC mode, and even one individual in Nepal uses around 208 plastics bags in a year. I mean, so these all plastic bags are mostly made up of polymer called polyvinyl chloride or polyethylene, which are non-biodegradable. Single plastic bag, which is non-biodegradable, it takes around 500 years to degrade. So it contaminates country, streets, sidewalks, forest, even popular trekking routes of the Himalayan region. I could find some research work that had done in Nepal. So what the problem with this non-biodegradable plastic or non-biodegradable polymers is that they come in contact with the water, and they yeah.
We can't see your
Hello?
slides.
You can't see your slides?
Yeah.
Oh, really? I shared. Oof. Sorry about that. Okay. Share screen. Host disabled participant share screening. I'm trying to share the screen.
And now we can see the screen. Now your host for the.
It says that. Okay. Hang on. Can you see it now?
Yes.
Yes.
Okay. Yeah. So sorry about that. So. So yeah, I could find some publications related to non-biodegradable plastic, and that was conducted in Nepal, and I found out that yeah, the plastic has entered everywhere. The article on the left hand side, it mentions about the microplastic detected in the Fewa Lake. So what happens is that when it comes in contact with the water and it converts into some microparticles of plastics, they entered into the ecosystem, and it literally plagues up everything. And they have found in meat, they have found in kidney, and everywhere. Even not only that, even in Everest they found a microplastic, and when I read through this paper, the microplastic is mostly non-biodegradable, which is polypropylene and polyethylene. As I said before, it takes around 500 years to degrade. So yeah, it's just not that great. So before jumping into whole biodegradable related polymers and application, as I said, I'm based with drug research, and for drug delivery, both of polymers are vital, both biodegradable and non-biodegradable, and biodegradable, they have got a specialized backbone, polymer chain backbone with a amide and ester functional group, so that enzymes or whatever bacteria, when it comes in contact with them, it just clips them, and it converts into some other like carbon dioxide and water, and so that it returns back to the ecosystem. Meanwhile, non-biodegradable doesn't have that. It has long hydrocarbon chain. It's really difficult to degrade. That's why it stays in ecosystem forever. So for drug delivery, both the polymers are used. The one in the left hand side called Glidel, it's a carmosutin, it's an anti-cancer implant. When it is used for the treatment of brain cancer. And there are some on the right hand side, which is implanon. It is made of non-biodegradable polymers, which is called ethylene vinyl coacetate. It's a non-biodegradable polymers. So the thing about biodegradable polymer is that it decomposes naturally. So, and they have got, as I said before, it has got amide, ester, and ether backbone. So and because of that, it is susceptible to very enzymatic degradation by bacteria, fungi, actinomycetes, and when it's inside the body, it is degraded by enzymes. So first, it biodeterioration. The process is biodeterioration, and it converts into certain fragments. Again, it gets assimilated by enzymes or bacteria, and then eventually it gets converted into carbon dioxide and water. So broadly, if we go to if we classify biodegradable polymers, they are either natural origin or synthetic origin. So even in natural, either it is extracted from the biomass, like they just extract from the plants related stuff, or either it is natural or genetically modified organisms. So when you moved on to this extracted from biomass category, there are thermoplastic starch, cellulose derivative fibers, chitin, gums, and this chitosan is a really popular polymer, biodegradable polymer. It is widely used in drug delivery and other application. A lot of in 90s and 80s they made a lot of mucoadhesive particles, and not only that, it is there you can find the chitosan tablets just to lower the cholesterol and lipids. When person has the hyperlipid, they just prescribe chitosan tablets. And there's some gluten. Gyn is a polymer from glycoprotein polymer. It is really widely used these days, and there are lipids. Among natural or genetic modified organism related biodegradable polymers, there is polyhydroxyalkanoates. They find out a special type of bacteria to synthesize, and polyhydroxybutylene and polyhydroxybutylene valerate. These are relatively new biodegradable polymers compared to other ones. And coming towards synthetic, it also has both bioderived monomers. PLA is very widely used. My current work is heavily involves this polymer PLA. It is isolated from corn, and there's PLGA. It is similar to PLA, synthesized version of PLGA. It degrades a bit faster than PLA, more soft. And the implant which I mentioned earlier with that anti-cancer carmocytin drug, anti-cancer drug for brain tumor, it is based on this polymer PLGA. It is easily metabolized by enzyme. And coming back to purely synthetic, there are PCL, polybutylene succinate adipate, and polybutylene succinate. The bottom one is polybutylene succinate. So yeah, and this PCL is really cheap, and you get a lot of materials based to this polymer PCL. It is easy to process. I'll be talking further how these polymers are processed. It is processed through a process called Halt melt extrusion or injection molding. That's how we get the plastic of different shape, which I'll be talking further. And glass transition below the glass transition temperature, polymer behaves like a glass. It's brittle. Above the glass transition temperature, it becomes amorphous. So yeah. And there is tensile strength. Tensile strength basically means it's the strength of the polymer. There is a standard method to do that. These are degradation time. How long does it degrades? I mean, there is for this as well, there is a standard method to determine that. And crystallinity refers to a toughness. It determines how tough will the polymer be, how brittle will the polymer be. So polymer, as you can see in this slide, some polymers are really tough, some polymers are really soft, and to achieve to target one application, usually polymers they are made of blends. I mean, what does it mean is that you take one polymer, you take another polymer, you mix it together, you process it through it, and you apply and you test it. You run through some standard tests, which I'll be talking further, and then you produce a more like suture or mulching material, or any food packaging material, or drug delivery systems. And yeah, PLA it's I think in terms of biodegradable polymer, after polycaprolactam, polylactic acid is the most widely used biodegradable polymers. So the problem with PLA is that it's brittle. If you use as it is, it's brittle. It's tough, but it's brittle, which means that it's not flexible. That for that you need to blend with certain polymers, and we have been working a lot with these blends. And even in the article, we can find there are a lot of blends, and even making blends, they are not that compatible. Sometimes you have to use compatibilizer, and sometimes you have to use the initiator to compatibilize it. Though now in the next slide, this is the way how we make blends. So the principle is that this is an injection molding machine. That's me on the left hand side, doing some extrusion and injection molding and making some blends. So the principle of this injection molding machine is that you put a pellets, you put a polymer system, it gets passed through a heated barrel. So here it's you put your polymers, it gets, this is really hot. You set a temperature above the melting point of the polymer, it gets passed through it, and you mold to a certain shape. And this is how you make a blend. First, there are two processes. There is a melt extruder. First, you pass through that, and you make a blend, and you make a pellet. And after that, you put it through here, and it passes through the hot melt barrel, and there is a hydraulic press, and you can set a mold. That's how you get to see this all shape and everything, whatever shape it is. You just make a mold like this phone, you will get a shape of this phone, because the molten mass get expelled into that mold, and it attains a definite shape. And for characterization, there are a lot of characterization involved, to say, oh, okay, we got a decent blend, and we can take it further. These are the tests. And some of the stuff is used in microbiology. For example, this is scanning electron microscopy. It's a general instrument which is used for any purposes. So the most important bit for this polymeric blends is tensile testing. What they do is that they take a polymer of certain, like they say dog bone specimen, and they put in this clamp and they pull apart. When they pull apart, they get this, sorry, they get this curve, which is called stress and strain curve, which they call it stress and strain curve. So as I said, if the material is brittle, there is a huge stress involved, but you don't have sufficient strain. So the curve is it plummets. If it is flexible, if it is ductile, for example, like PBAT or PCL, which are polycaprolactam, they are ductile. They don't have much strength, but they can be extended like a rubber. As long as you can, this curve will literally go with a bit for further distance. So what do we do is that we take a brittle polymer, we take a ductile polymer, make a blend at certain ratio, and we get a decent profile. This is the profile we want, with certain strength and with certain ductile properties, so that it can be molded to any shape. So this is the theory. And after that, we pass through instrument like differential scanning calorimetry. We see, okay, how the crystalline domain had changed, how the amorphous domain had changed. Same with the XRD. XRD determines the crystalline structure of the polymer. And the last one is FTIR. FTIR determines the functional group. If there is any interaction involved between the functional group of the polymer, the the functional group, the peak attributing to that functional group shifts. And that's why, okay, there might be some hydrogen bonding, there might be some other level of interaction involved. So now the question is that, can we replace all non-biodegradable polymers by biodegradable polymers? Sadly, the answer is no. I mean, because the issue with the biodegradable polymers is that yes, we can achieve up to certain strength, but compared to non-biodegradable polymers, they are not that strong. For example, for some application, we cannot replace. For example, aviation industry, there are certain parts required for aeroplanes we can't replace with biodegradable polymers. Same with drug delivery. There is something called bone cement. After you have a fracture, to connect the two bones, they put a cement, which is made up of polymethyl methacrylate. So you can't have there's no way you could replace with the biodegradable polymers. Same with silicon, polyurethane. So that's why for some applications such as orthopedic, vascular gloves, biodentistry, and some drug delivery systems, you can't have, there's no way you can get away with non-biodegradable polymers. So this was one example for drug delivery is my PhD work, where we had made a non-biodegradable based implant. So the implant had to be pulled out after a certain time. So we wanted to have a certain strength. So there was no way we could add biodegradable polymers, because if we had made implant with biodegradable polymers, we had to pull that out at some stage, and by pulling out, because the biodegradable polymers would start degrading, so the pulling out would have been really difficult. So we made an implant, and the implant was quite good, and we filed the patent. So it's the patent has been granted. Now it's in the stage of commercialization. So now, in context of Nepal, I just Googled it. The only thing I could find out was for this plastic bag, so which is supplied by Joy Traders, I think, and I think it is made of a PLA as well. I'm not sure how widely it is available in market, but I saw this. I mean, it's certainly a good start, but there is a huge potential I see in. I mean, Nepal has a lot of forestry. I mean, a significant portion of land is covered with forest, so there is a huge opportunity for this biodegradable polymer related activities, whether it is a basic research or whether it is a applied research, or there may be a possibility of forming a company. I don't know, but I see there is a huge possibility, because we have a lot of problem, lot of non-biodegradable waste. The silver lining is that there are some decent leaders we have elected. I mean, like Balen, I think he would be interested to shifting from non-biodegradable to biodegradable polymers. The These days, this lignocellulosic biorefinery has been really popular. So what they do is that they take a cellulosic biomass, whatever it is, they process it, and they can be applied to many things. I just reviewed one grant where the candidate wanted to use this lignocellulosic material, process it, and wanted to make biosensors. So it was incredible. So what we could do is that they isolate the cellulosic material. The good thing about cellulose is that you can functionalize it, you can treat it, treat accordingly to functionalize it and use it for various application. Another thing is agriculture. With this commercial agriculture booming in Nepal, I see they use a lot of mulching. I'm not sure whether they use biodegradable materials or not, but maybe they use PVC, which is really not biodegradable, and eventually it will hamper the fertility of the soil. There will be microplastic going on. So definitely there is a possibility. And yeah, if we have this lignocellulosic biorefinery, you can use whatever you can, the waste from house, waste from plants or whatever, you process it, you convert into the polymeric material. And yeah, and food and packaging, of course, plastic bags, it's the example on the right hand side. And formulation and drug delivery, unfortunately, all the excipients we import, I don't know how feasible it is in terms of, definitely there should be some cost effective analysis, but to my knowledge, when I worked in Nepal, there was not a single industry who produce raw materials. There are a lot of raw materials which are biodegradable based polymers are used, like starch, HPMC, hydroxypropyl methyl cellulose based system. I'm not sure if there is any industry which produces raw material of these materials. And medical devices, and still I don't know, uh, when I have a chat with my pharmaceutical fraternity in Nepal, they said that there is no company for sutures. Biodegradable sutures can be one option. Who knows? I mean, we might have some plant which way we could isolate some functional materials, and down the line, I don't know, yeah. So this is all about the biodegradable materials. So yes, that's all about this. Yeah,
Thank you. To open the
yeah.
floor
I
for
was
questions.
should I should okay stop sharing. Yeah,
Hello, Prabhat bhai. म
yeah.
रोजली
Hey, hello, Rose.
के छ
Hello, सब ठीक छ. How are you?
मलाई ठिक छ भाइ
हजुर?
This biodegradable polymer, especially the one which you are working, is the polylactic acid, right?
हजुर. Yeah.
So can it be used in edible coating if it's biodegradable?
Edible goodie. Yeah. No, for edible coating,
Can
no.
can we eat?
So although it's yeah. So yeah, I get your question, Rosalina. So for although it's a biodegradable coating, when you compare the biodegradability, it has got some it takes about considerable amount of time to biodegrade. I would rather switch it to some cellulosic polymers which go into a gut and it get solubilize or dissolve into water straight away, physiological fluids straight away. For example, there are some cellulosic polymers widely available in market. There are some starch or and even there's something called methyl cellulose. That would be more appropriate, I think.
And is it cheap, this polylactic?
PLA, yeah, compared to PCL is the cheapest in commercially available. This polyester polymers, polycaprolactone is the cheapest. PLA, unfortunately, is not that cheap. It is available from a American company called NatureWorks. So, and there maybe, I don't know. I haven't looked at through suppliers from China. Maybe from this, if we go through the suppliers from China, maybe this would be cheap. Yeah.
Because I was thinking if I could use it in edible coating, so it
Yeah.
would be better, it would be cheap.
Yeah. So yeah, yeah. Yeah. As I said before, methyl cellulose or cellulosic material would be more appropriate for edible coating.
Yeah.
and they're flexible as well, because the coating should be plastic, otherwise it will peel off from the whatever food material you will be coating. So the cellulosic polymers offer way more better flexibility compared to just PLA. Even if you get the PLA, even if it was cheap, you had to make a blend before coating into any food materials. Yeah.
And regarding the tensile testing that you showed in your presentation, what is the instrument that you measure the tensile strength?
So it's called tensio texture analyzer, and it can be so how does it work is that you make a dog bone like a flat film, I wouldn't say film, like it to be flat, and you just pull it apart until it breaks, or until it is deformed significantly, and you get a strain and stress curve. So it's in Nepal, I think KU might have that instrument, but I don't know about the load cell capacity. If you have a thin film, even 5 kg to 15 kg load cell will do the job. But for polymers like PLA, you need around 150 kg of load cell. I think KU might have that instrument, Rosalina.
Because in our research also we need to calculate this stress, I mean the tensile strength of this edible protein. So I was wondering if we could use machine for that purpose.
Yeah, absolutely. Yeah. And some packaging industry should have this. I mean, if they do basic R&D, they should have this machine. The foil company or this plastic company, they should have this instrument. Yeah.
Okay, that's it from my side.
Yeah, no worries.
So, Prabhat,
Yep.
I have a small question regarding PLA. So in Futung, they do a lot of 3D printing. In that 3D printing, PLA as a polymer, and they devices a lot of prototype with that PLA.
Yeah.
So do you know like after how many years that PLA or that device get degraded in the nature?
Yeah. So, Prajwal, that PLA can be, there are two isomers, L isomers and D isomers. D isomers degrades, it takes a very, very long time. If it is L isomer based PLA, it might degrade within 10 years, but it has to be within certain particle size. I mean, if you have a PLA of this size, it may take even more time, maybe 20 to 30 years. But so what they do is that there is a definition for biodegradable by something called it is called ASTM, and for that what they do is that slice into some film, and they put some into some agar like bacteria and they see they see how much it's left, and that's how it is defined. But it doesn't mean that if you have the PLA of this material, it will degrade within 10 years. It has to go through some combustion cycles where they shred it and they convert it into particles and they combust it.
So if the size is bigger, it may take like more than 20 years.
Yeah. It could be more than 20 years. But the advantage is that when you process through industrial this, I don't know what's the terminology called. They go through the process, they shred it, and they use some fermenter to convert it into to degrade it. If you process through that, it will be just within a couple of year or maybe 2.
Okay, thanks.
Yeah.
Thank you, Prabhat. Do you have any questions regarding PLA or biodegradable polymers?
Maybe I was surprised with the example that he has shown and the first slide that not plant, it is non-biodegradable.
Yeah.
So
No,
it's a contraceptive, right?
yeah, it's contraceptive. It is made up of a polymer called silicon, so it's not biodegradable. Silicon is not biodegradable either.
How?
Yeah. So there is another contraceptive called implanon that is also not biodegradable because they had to be. I think they stay in the body for around 5 years, more 3 to 5 years. So in that case, they prefer to use non-biodegradable system. If they want to have release for a very prolonged period, they prefer non-biodegradable because you can't achieve by biodegradable system.
Yeah, we don't have any question from our side.
Yep.
Yeah, I think that's all the questions for today. So it's been a pleasure being with you all today. I would like to appreciate the effort and time of our guest, Dr. Pawal Prasad, for delivering this work, his work and this talk today. So we hope that this talk has been informative to us all. And now I would like to conclude today's seminar.
Thank you. Thank you very much. It was great to meet you all.
Thank you.
See you. Bye.
Bye-bye.
Bye.